So we're still in section 12.1. We're still talking about vector valued functions. We're just going to do a little bit more with them today. So let's look at an example like one of the homework problems that we just talked about. So we have r of t, our vector valued function, and that is 3 sine ti plus 4tj plus 5 cosine t k. And we want to sketch this curve. So how are we going to go about doing this? What do we know? What can we figure out? So we can look. Scott says we can look at the projections in the coordinate planes. So so let's see. In the SK. Thank you. So which planes do we want to look at first? In the XZ plane. If we project this onto the XZ plane, we get we have x equals 3 sine t, and y equals 5 cosine t. Z, thank you. Z equals 5 cosine t. What does this give us? An ellipse. So we have an ellipse. We got an ellipse because we have different, we have a 5 and a 3. So if we project this onto the XZ plane, we get an ellipse. So if we have an ellipse in the XZ plane, what does this 4tj do to our curve? So Tian is doing this, circling his hand and going up. So parallel to the XZ plane, our position vector is going to travel in a circle. So the tip of the position, an ellipse. The tip of the position vector is going to travel in an ellipse, and as t increases, it's going to move along the y-axis. So our curve is going to be what we call a helix, and because this is an ellipse, we get an elliptical helix. So let's do a quick sketch of what this is going to look like. And I don't want an arrow here. And then helix is this form for a vector valued function. It's going to be a good thing to recognize a helix when you see it. When you have some kind of circular function between two variables and a linear function in the third component, you're always going to have a helix. And anybody have an idea of why helixes are important, or an example of why helix might be important? DNA is a helix. So that's the shape. If we wanted to talk about the shape of a helix or a DNA mathematically, we'd be talking about something like this. How about you physics people? Springs are helixes. What about charged particles? What happens when a charged particle moves in a magnetic field? So Scotty says it goes in a circle because the magnetic force is perpendicular to the velocity, right? So what happens if a charged particle enters a magnetic field with an initial velocity? It travels in a helix. So charged particles in magnetic fields travel in helixes. So that's one reason. Another reason why this is important to recognize this. They come up a lot in electromagnetism. So we have, if I were to, I'm going to sketch out my ellipse. So here in the XY plane, which is going to be my major axis, the X or the Z. Z is going to be my major axis. So I'm going to have an ellipse that looks, it's not going to be a beautiful sketch. But here's my ellipse in the YZ plane. And I'm going to, in the XZ plane, and Y can be anything. So this is the kind of elliptical cylinder traveling along the y-axis, and our particle is going to start at t equals 0, where if we imagine a particle moving along this curve at t equals 0, where are we going to start? Where are we going to be? Z equals 5, so we're going to start here, and then we're going to move from here. We're going to move into the positive x direction. So our little particle is going to go along here, and then it's going to go back here, and then it's going to go along here, and then it's going to go back on this side, and then it would go along here, and it's going this direction, this direction. So the red line is a sketch of the helix that this vector valued function describes. Does that make sense? So what I want to do next is on page 839. Numbers 89 through 91. These are true-false questions. So what I want you guys to do, I want everyone to look at these, decide if the answer is true or false. Either way, come up with an example or a counterexample. If it's true, come up with an example. If it's false, if it's true, come up with an explanation. If it's false, come up with a counterexample. And then in a little bit, we're going to talk about these. While you work on them, I'm going to write the problems up on the board here. And if you want to work together, if you want to discuss as a group, that's fine. yeah, 89 through 91 is what we're going to be talking about in just a minute. Everybody done? Yes, everybody's got answers? And remember Calculus the Musical next Monday? Last year, you guys remember Robin Rebold? He was on stage. He was so proud of himself. All right, let's look at these. So we're looking true or false. So if f, g, and h are first degree polynomials, then the curve given by x equals f of t, y equals h of t, and z equals g of t is a line. Does everybody agree? True? And says that's the answer in the back. So the way I looked at this, it is true. The way I looked at this is if these are first degree polynomials, if f, g, and h are first degree polynomials, we could write x equals, let's see, at plus some constant, some line, y equals bt plus some other constant, and z equals ct plus c3. And what kind of equations are these? Parametric equations for a line. So that's if we wanted to provide a kind of a more of a formal argument, that we could say this would be our argument, and this is a line. All right. The second one, if the curve given by these parametric equations is a line, then the component functions are first degree polynomials. False? Did you think false, Charles? You thought true? So wait. What did you say, Andrew? If they're all the same. So if we had, that's an excellent counterexample. So if we had f of t, what was yours, Andrew? Did you say like t squared? F of t equals t squared. G of t equals t squared, and h of t equals t squared. Then we have x equals y equals z. And that gives us, we'll have a line. Make sense? Is that along the lines of what everyone was thinking?
No.
Something? No?
We did the argument that one of the equations could just be a constant, and you have to add the t values in it.
One of them could be a constant.
Yeah, just 3.
So z equals 3.
Yeah.
That would work as well. All right. Oops, that's not what I want to do. Do that. So two objects are traveling on these two paths, and we want to know if they'll collide. True or false? False. And why is this false? No. So Charles says for all t, the I components of the two vectors can never be equal. Because if you try to set those two equal to each other, what do you get? 2 equals 0. So the I components can never be the same. And Tian, you said you made a good kind of intuitive argument also. What did you say? That essentially what you said. They cross the same point, but not at the same time, right? That's what you were saying. So this one is false also. I forgot to write the answer on the last one. All right, let's look at the last one. So this curve described by this vector valued function, t squared I plus t sine t j plus t cosine t k, lies on the paraboloid x equals y squared plus z squared. Is that one true or false?
True.
Anne says true. Does everyone agree? So what is your argument, Anne?
That in the paraboloid, like it's that thing.
So Anne says a paraboloid is kind of this thing, yes?
Okay. So then, I know that there has to be circles in one section of that equation, and then the other one paraboloid. That looks right.
So Anne says we have to have circles parallel to one coordinate axis, right? And parabolas parallel to the other coordinate axes. And it kind of looks like that should be the case. So if we wanted to, did anybody do anything different? Did anybody write any equations?
You squared second 2, things from j into k.
Yes.
And it equals x.
So Tian says let's square the y and the z.
Yeah.
So if we say y squared plus z squared equals t sine t squared plus t cosine t squared, we get t squared times sine squared t plus cosine squared t. And that just is 1, so that's just t squared. And t squared is x. So y squared plus z squared equals x. So that's how you could verify it with some equations. Does that make sense? Any questions? All right, homework. Page 838. So are you guys excited when we're done with this class? You'll be able to look at that calculus book and say that you know everything in there? There you go.
That's it?
That's it. We're kind of easing into things this semester.
I love it.
You love it? That'll change a little bit.